Hello, Luke. Welcome to lesson 38. And today we're going to be talking about ratio problems. All right. So let's get started. So, what is a ratio? All right. What is a ratio? Well, the simple answer would be that a ratio is simply another way to view fractions. All right. It's another way to think of fractions. So any fraction that you want to give me, let's just take the fraction 1/2. This is also a ratio. It's just another way of looking at this, another way of understanding fractions. All right. And it is interesting because in algebra, it does seem like we have a lot of uses for fractions. We've already talked about fractions and how they indicate division, right? If I have 4 halves, we could think of this as being 4 divided by 2, right? Which, of course, is 2. So 4 halves is equivalent to 2, right? So this fraction bar, we often think of it as division. All right. Well, ratios, that's just kind of a third way to think of this fraction bar. All right. So before we get into what the understanding of this fraction would be in terms of a ratio, let's just quickly look at what a fraction is in kind of the more common understanding. All right. So if we take the fraction 1/2, just quick review. What does this mean? All right. The thought behind it. And let's just use a circle here. We'll call it a pizza, right? And this 1/2, when we're thinking about it as representing a part of a whole, the denominator, in this case the 2, tells us how many pieces we're going to cut the whole into, right? So in this case, we'll be cutting the whole into 2 pieces, right? And I'm going to try to do that evenly. They should be even pieces. So we'd split it right down the middle, right? And then the numerator would tell us how many pieces we're interested in, how many pieces we're going to eat in this case. So if we have our pizza and we've just cut it into 2 pieces, and now we're going to eat, we're going to eat this side. All right. So we kind of eat this side of the pizza. All right. And we'd have to be pretty hungry to eat half the pizza there. So, but when we think of fractions, this is often the way we kind of think of them. They're parts of a whole. All right. We're taking one out of the 2 pieces. Okay. Now, the thing I want to remind you of is that fractions can be written in an infinite number of ways. All right. So if I take this fraction 1/2, we've learned in the past that I can multiply that fraction by any number I want, so long as I multiply the numerator as well as the denominator by that number. So let's say I multiply it by a 4, just for example. We multiply it by a 4 over a 4. Okay. Well, 4 over 4 is equivalent to 1. So we're really only multiplying this fraction by 1, which of course doesn't change it. But in this case, we'll notice that the numbers actually change. So 1 times 4 is 4, 2 times 4 is 8, and so we end up with 4/8. So 1/2 is equivalent to 4/8. Okay, the values of these fractions are the same, and this is just basic review. All right, this concept becomes very handy when we try to find common denominators, as we've done in the past when we're trying to add or subtract fractions. But in this case, I just want to remind you that this fraction 1/2 can be written in terms of other numbers, but still has the same value as 1/2. All right, as we have here. And again, if I were to then, transpose this up onto our figure here, we'd have 4/8. Well, we could then divide this up into 8 pieces now, right? So we'd have to cut it kind of this direction. That would give us 4 pieces. And then we'd have to cut it this direction. Now we're up to 6 pieces. And then we go this direction, right? And now we're up to 8 pieces, 8 equal pieces. And now if we're going to take 4 of them, well, that means we're taking this one and this one and this one and this one. And lo and behold, I've still taken the same amount of pizza. I've still eaten half the pizza. All right. So that's just a visual aid, just kind of demonstrating that this 1/2 and this 4/8 are in fact representing the same amount. They have the same value, they just have different numbers. And I could continue with this. I could take this 4/8 and just, multiply it by a 2 in the numerator as well as in the denominator, right? And that would give us another equivalent fraction. So 4 times 2 is 8, and 8 times 2 is 16. And we end up with a third equivalent fraction, 8/16. Okay, and to get to that, boy, we're really going to put in a lot of lines here, but then we would be cutting all of these in half again. So that would be maybe 1, and I know these, you're going to have to just imagine that these are exactly the same size. I know I'm not perfectly accurate here. And there, and ooh, that one I don't like. Started on the edge here. And, ooh, but we want it straight. We'll start it about here, go up to here. Okay, so something like that. So that would be 16 pieces. And notice how many we're taking. We're taking 8. And so we would be taking, 1, 2, and 3, and 4, and 5, and 6, and 7, and 8. So again, we're taking, this section of the pie. Right? We're still just taking half the pie. We just cut it up into smaller pieces. Okay? So 8/16, 4/8, and 1/2, they all represent the same value. They are what we call equivalent fractions. Okay? Notice the 8/16 could be reduced down to the 1/2 if we wanted to. All right? So that's just a quick reminder that with fractions, we have infinite numbers of equivalent fractions, all right? Because that's going to be important. That's kind of the basis for these ratio problems that we're going to be looking at, all right? So now let's get down to what a ratio is, all right? Let's look at a 1/2, all right? And we're going to think of this as a ratio. And when we think of things as a ratio, we read these fractions a little bit differently. Instead of reading this as 1/2 or 1/2, we actually read this as 1 to 2. Okay? If I have the fraction 3/4, or I should say the ratio 3/4, I'd read that as 3 to 4. Okay? That's how you would read them as ratios. And what we're actually doing with ratios is we're comparing two numbers, all right? We're saying for every one of something, we have 2 of something else, okay? So for every 3 of something, we have 4 of something else, all right? And those somethings could be whatever we're interested in. So maybe there's, in a certain classroom, for every 3 boys, there are 4 girls. We would read that as 3 to 4. 3 boys to 4 girls. Okay? And we'd write it as a fraction, at least that's what it looks like, but we'd call it a ratio. And all we're doing is just, again, we're just comparing 2 groups. We're saying we have 3, for every 3 boys, we have 4 girls. So if we had 6 boys, we would have 8 girls. Does that make sense? I'm just doubling it. 3 boys to 4 girls. Well, if we have 6 boys, well, then you're going to have 8 girls. If I triple it, I'd have 9 boys to 12 girls. Okay? So a ratio is we're just comparing kind of the sizes, you might say, of 2 different groups. And we're writing them as a fraction. All right. Now that's kind of difficult to envision in terms of our pie up here, isn't it? I mean, if I think about this 4/8, for example, we're saying for every 4, I have 8. Well, what would that actually mean? It kind of just would mean that for every 4 pieces that I'm taking, I had 8 total, which doesn't make a whole lot of sense, or it's not very useful to us when we're talking about pies. But when we talk about ratios, it actually is useful in solving problems. So again, ratios, they're just kind of a slightly different way of perceiving fractions and what they mean. Okay? So there is an important concept that I want to go over now. and that has to do with fractions. So, we're going to go back to these equivalent fractions that we talked about earlier. Sometimes it may be difficult to determine whether or not two fractions are equivalent without actually reducing them both to their lowest terms. So let's just say I gave you the fractions, 1/8 and, I don't know, well, we'll keep it somewhat simple. We'll just, let's get rid of the 1/8. Let's go to something a little bit easier just to demonstrate. Let's go actually to our 1/2. We'll go back to the 1/2. That's a nice easy one. And let's say I had another fraction that was maybe, 3/6. Okay. Now, you might right away recognize that this 3/6 is in fact equivalent to 1/2. If I were to reduce this 3/6, you could do that in your head and recognize that 3/6 is the same thing as 1/2. So they are equivalent fractions. But let's just pretend for the sake of the argument that you didn't recognize that. You didn't recognize that these were equivalent fractions, and you're trying to figure it out without reducing. All right? There's an important concept when we talk about equivalent fractions, and that is if we cross multiply them, all right? And by cross multiply, I mean we take the denominator from one and we multiply it by the numerator of the other, okay? And then we take this one and we multiply it by the denominator on the other side. And we kind of form this cross. That's why we call it cross multiplication. But if we do that, what happens? Let's take the 1 times the 6. Well, that gives us 6. Then let's take the 2 times the 3. That gives us 6. And lo and behold, they actually give us the same answer. 6 equals 6. Okay? And that is true for any two fractions that are equivalent fractions. So that's a wonderful little concept there. So if we take even this 1/2, and we know that 8/16 is an equivalent fraction to 1/2. Let's try that out again. So 2 times 8, well, that's 16. Multiply the 1 by the 16. That's also 16. 16 does, in fact, equal 16. All right? So if I have, maybe something just a little bit harder, let's try like a 3/4 and a 15/20. Okay? It might not necessarily jump at you right away that these are equivalent fractions. So let's just cross multiply. What's 4 times 15? Well, 4 times 15, if you want, you can do it off on the side here, is going to be 60, right? And 3 times 20, well, that one we should be able to do easily in our head. That's going to be 60 as well. And lo and behold, 60s are what we get for both of them. Therefore, 3/4 and 15/20, they are equal. They are equivalent fractions. All right, so let's take this one step further. So, one more thing we need to talk about, another term that we need to get out of the way. If I have two fractions that are, in fact, equivalent, so such as maybe like this, right? 3/4 and 12/16. If you wanted to cross multiply these, you would find that these two are equivalent. So if I set these two equivalent fractions equal to each other, all right, we have something that looks a bit like an equation, right? We have a fraction on one side and we have a fraction on the other side connected with an equal sign, all right? When we have something like this, we have a special name for it. We call this a proportion. Proportion. All right, so whenever you hear somebody talk about a proportion, you should right away think about two fractions being set on either side of an equal sign. Okay, and these fractions, I keep saying fractions, but in fact, when we're dealing with proportions, we're thinking of these fractions in terms of ratios. All right, that's kind of the way we think of them. So we have one ratio that's being set to an equivalent, set equal to an equivalent ratio. Okay, so when we have these proportions, we recognize that if we cross multiply these two fractions, we should end up with the same number, right? And this is important because sometimes they might give you an unknown. What if I don't know this denominator? We'll call it an x, all right? Now we really have an equation going here with an equation with one unknown. And if we recognize that this equation is a proportion, we can now find the value for x fairly easily. And we can do it by cross multiplying. So we'll take the 4 and we'll multiply it by the 12. And that should be equal to the 3 times the x. So if we take the 4 times the 12, that's 48. And we'll set that equal to the 3 times the x, right? We're just cross multiplying here as we did earlier, only now we can't actually multiply 3 times x. We don't know what x is. So we end up with 48 is equal to 3x, all right? They have to be equal because we're assuming that this equal sign isn't lying to us and that these are equal proportions. So let's solve this equation now. Now we just have an equation in one unknown. So we can divide both sides by 3 in this case. 3's will cross out. We end up with x. 48 divided by 3 is what? 16. All right, so x is equal to 16. And notice that's what I erased up here. This was a 16 before. All right, so the moral of the story here is that when we set up ratios on either side of an equal sign, we can solve them by cross multiplying. Okay, we can solve them by cross multiplying. All right, so let's try some story problems now that deal with proportions and ratios. All right, so let's try a story problem here. If the story problem is the ratio of girls to boys in the classroom is 3 to 4, if there are 15 boys, then how many girls are there? All right, so the ratio of girls to boys in the classroom is 3 to 4, which means that for every 3 girls, there are 4 boys. All right, so obviously we're going to have more boys than we have girls. Okay, 3 girls to every 4 boys. All right, so let's go ahead and try a story problem now. So if the story problem is the ratio of boys to girls in the classroom is 3 to 4, if there are 15 boys, then how many girls are there? Okay, so the ratio is 3 to 4, which means that for every 3 boys, we have 4 girls. All right, hopefully you see how that coincides. The 3 boys to girls. So it's 3 to 4. 3 boys to 4 girls. Okay, so for every 3 boys in the room, we're going to find that there are 4 girls to those 3 boys. Okay, so now if there are 15 boys total, then how many girls are there? Okay, so to set this up, we're going to set it up as a proportion, which remember is just 2 ratios set on either side of an equal sign. And what are we comparing? That's really the first question here. What are we comparing in this story problem? Well, in this story problem, we're comparing boys to girls. So I'm going to use B to represent boys and G to represent girls and just go, okay, I'm comparing boys to girls. Now, you might be willing to say that it's girls to boys. That's fine too. We could compare it either way. We can put boys on top or we can put girls on top. Either way is fine, all right? It's just going to change how we set up the problem a little bit, but we're going to get the same answer in the end. All right, so boys to girls. Now, because we're working on setting up a proportion here, all right, that means we need an equal sign and we need another fraction on this side, okay? Now, this is where we have to be very careful, okay? This is where we have to recognize that the one side here, we'll call it this side here, this is the, we'll call it the ratio side. And this side, well, we'll call it, and maybe I'll just box these. We'll call this side, we have to give it a name here. Let's make up a name. Let's call it the reality side. Okay? So this side is the ratio. This side is, in reality, how many of each do we have? Okay, so hopefully that kind of makes sense. It's what we're looking up here, The ratio of boys to girls in the classroom is 3 to 4. Well, that's the ratio. That's not telling us how many there are in the classroom. It's just telling us that if we take 3 boys and pull them out of the group, we can then also find 4 girls that we could pull out of the group to match those 3 boys. Then we could pull out another 3 boys and find another 4 girls to match those 3 boys. And we could pull out another 3, and then we just keep on going, right? So it's not telling us how many boys and girls there are in the classroom. It's just telling us that for every 3 that we find, we'll also find 4 girls, okay? So that's the ratio that we're talking about here. So it's 3 boys to 4 girls. So that would be this B and this G over here. Now, this other side, this is the reality side. This is, okay, in reality, how many of each do we have? And that's kind of the second part of the story problem. If there are 15 boys, then how many girls are there? So we know that there are 15 boys. That's the reality, okay? So we have the ratio side, we have the reality side. Now, the key to this whole problem is keeping the comparisons straight. So in this this ratio side, we have the boys on top. That means the boys have to stay on top over here. All right, so just to make sure that that's clear, we're going to represent that as, well, we'll go back to our dark color here, but we're going to represent that as a B over here as well. Boys over here, and then girls over here as well. Okay? So that the B and the G, they're on the same side of the fraction sign, okay? And over here, we wouldn't have to do it both ways, but just to show you that both ways still work, over here, again, we have our ratio side, and then over here, our reality side. We're just going to make sure that we put girls on top and boys on bottom again, all right? Just matching both sides, all right? Okay, so once we have that clear, we can now fill in some numbers. So the boys and girls, well, the ratio boy-girl is 3 to 4. 3 boys for 4 girls. So we can replace the B with 3, the G with 4. All right. Then we have our equals. Now we have, in reality, how many boys do we have? Well, they told us that. They said there's 15 boys. So we can put the 15 on top. The G, they did not tell us how many girls there are in reality. That's the question. That's what we're trying to find. So that stays as a G. That's our unknown. Okay. So now we have it as a proportion with one unknown, and we can cross multiply to solve. So we'll cross multiply these two. We have 3 times G, which is going to be 3G, right? And then we have 4 times 15, where if you multiply that out, that'll be 60. All right. So now we can say, let's divide both sides by 3. And we end up with a G is equal to 20. So that means if there are 15 boys, there must be 20 girls in the classroom. Okay? And just to show that it would make sense, or that it would still get the right answer if we did it this way, let's do this side. So the ratio of girls to boy now is the opposite. We said this was 3 to 4, 3 boys to 4 girls. Well, if we switch that, it means that for every 4 girls, there's 3 boys. So it's 4 to 3. So this becomes 4 to 3. And then on the reality side, we don't know how many girls there are. They didn't tell us. They did tell us there are 15 boys, so we'll write that down. And lo and behold, we're just going to be doing the same thing. We're cross-multiplying. We have 4 times 15 is 60. Equal to 3 times G, which is 3G. We divide both sides by 3, and we still end up with G is equal, oh, that looks like a 6. G is equal to 20. So the number of girls is still equal to 20. All right? So hopefully that makes sense to you. The biggest thing that you need to remember is to first, before you start plugging numbers in, it's a very good idea to first plug in these variables that just organize the groups that you're comparing in these ratios, the boys and the girls. So first, before you deal with the numbers, set it up as variables so that you can see clearly that the boys are in the right spot, the girls are in the right spot, and then fill in your variables with numbers where you can. And just remember, the left side, we can think of that as the ratio side. The right side, that's the reality side. Okay? All right, let's try another one. All right, so let's try this one. The ratio of dogs to sheep was 1 to 20. If there were 500 sheep, how many dogs were there? All right, so why don't you pause the video, give this one a try by yourself, and then we'll do it together. All right, so let's see how you did. The ratio of dogs to sheep was 1 to 20. Now remember, we're trying to set this up as a proportion. Right away, we need to see that. Whenever you see it's the ratio, that kind of gives it away. When they say the ratio of something, right away you should think, oh, proportion. Let's set this up as a proportion. Okay, so the ratio of dogs to sheep was 1 to 20. So let's just right away say, okay, we have a proportion, which means we have a fraction equal to another fraction, or I should say a ratio equal to another ratio. What are we comparing here? Well, looks like we're comparing dogs to sheep. So we'll put D for dogs up on top and S for sheep on the bottom. Okay, which means then we also need a D for over here and an S over here. And you know what? Yeah, let's do a capital D. Just so that makes it even more clear, and a capital S. Just kind of demonstrating that these are the ratio side. This is, different, a different number for dogs than this number over here. This capital D is, in reality, what is the number of dogs that we have, all right? So we have D over S is equal to D over S. Okay, now let's look at the ratio. The ratio of dogs to sheep. What did they tell us? Well, dogs to sheep was 1 to 20. So it's going to be 1 over 20. Okay? Equals. Now, they tell us how many dogs there are in reality. No, they did not. Did they tell us how many sheep there are in reality? Yeah, there's 500 sheep. So we can fill that in with a 500. Okay? Now we're ready to solve. We've gotten it into one variable. So now we can cross multiply. This one's going to be pretty easy. We have 1 times 500, well, that's 500. And then we have 20 times D, well, that's 20D. And then we're going to divide both sides by 20, right? And zeros will cross out, so we have 50 divided by 2, which is 25. So we have 25 equals D. So how many dogs do we have? We have 25 dogs when we have 500 sheep when we have this ratio. Excellent. All right, well, hopefully that makes sense. Why don't we try just one more, and then we'll call it a day. All right, so for this last problem, why don't you go ahead and read it to yourself first, try to do it, and then we'll do it together. All right, so the problem is the ratio of dogs to cats in the barn was 3 to 9. There was a total of 12 dogs. How many cats were in the barn? So we need to recognize that we're talking about a ratio. So we need a proportion here. Okay. Then we need to decide what are we comparing. And it seems pretty clear we're comparing dogs to cats. So on the ratio side, we're comparing D, we'll say that for dogs, and C for cats. All right. And then we have the reality side. How many dogs are there total? Well, they told us there are 12 dogs, but actually I'm getting ahead of myself. We'll write it as a variable first. So we have our capital D for dogs, and then below that we'll have our capital C for all of the cats. All right, so now we have our proportions set up. We can start plugging in some numbers. So the ratio of dogs to cats in the barn was 3 dogs to 9 cats. So D over C is going to be 3 to 9. Okay, equals, they told us how many dogs there were. There were 12. They did not tell us how many cats. That's what we're trying to find out. And at this point, we have our equation. So we can do our cross multiplying. So we can cross multiply these. 3 times C would give us 3C. 9 times 12, that's 108. Then we can divide both sides by 3. And we end up with, let's see here, 336. So the number of cats is equal to 36 when we have 12 dogs. All right, very good. So I think we will stop there. In the upcoming lessons, we'll be working a little bit more with these and starting to make them just a shade more complicated. So really get into the groove of setting up these problems. Remember to set them up as variables first. I know it seems a little bit um, more work than you need to do right now when you do that, but it is very important later on. It'll make things a lot easier. So continue to set them up as variables, then plug in your numbers. All right. We will see you tomorrow.